Hello students. So, in the previous class we looked into the concepts of volume integral, and before that class we worked few examples on surface integral. For the time being we go to the vector calculus part, because that is also very important, and at the end I will try to cover the center of gravity chapter, where we have some formulas from integral calculus that will help us calculate center of gravity and moment of inertia. But for the moment I will start with the vector calculus section, which is also very interesting, and you can be able to relate the things which you have learnt in your scalar functions like limits, continuity and differentiability, integration of scalar functions, which we were doing up until last class. So, in the vector calculus as well these things are there, and we will see how we actually define the vector function and its limits, continuity, differentiability, things like that. So, today we are going to start with this chapter here. So, this here. So, scalar limit, continuity, differentiability of vector functions. So, this is what we are going to start with. All right. So, let me start a new page, and I am going to increase the thickness a little bit. Yes. So, today's topic is vector functions. So, what do we mean by vector functions? So, usually the function of scalar variable or scalar functions are written as y is equals to f x, where x is the independent variable and y is the dependent variable. Possible examples could be y is equals to f x equals to, let us say, x square plus 2 x plus 3, or f x equals to sin x or exponential x, any such functions which we have learned basically. So, those are the scalar functions, function of one variable. Now, how do we define the function of how to say it's vector functions actually? So, I mean, we know that vector quantity, they have directions as well as the magnitude. So, how do we define functions related to that? So, we can give a formal definition for a vector function. So, the formal definition goes like this. So, let D be a subset of set of all real numbers, and if for every t in D we can associate by some rule, So, what is this rule? I will define, but for the time being let us write it as by some rule a unique vector, say f t, then this rule defines a vector function. All right, of the scalar variable t, and here f is basically a vector quantity or a vector function for the variable t. So, f can be called as basically a vector function. So, one possible so we represent this. So, since a vector quantity has 3 directions, so I, j and k, we can be able to, with the help of I, j and k, we can be able to write a vector quantity or a vector basically. So, here this vector function f t can also be represented with respect to those unit vectors I, j and k. So, we represent or we write f t equals to f 1 t I f2t j f3t k, where I, j, k are unit vectors. So, basically along x axis, y axis and z axis. So, they are perpendicular to each other and they are the unit vectors. So, here f1t is a function of t, f2t is a scalar function of t, f3t is a scalar function of t. So, all of them are basically a scalar function of t, and while writing with the help of I, j and k, they constitute a vector function. So, one possible example could be, let us say r equals to f t. So, we write basically the vector function by r, and r is a function of t, and we write r equals to f t equals to, let us say I could write 2 t square I plus sin t j plus cos t k. So, this is one such example for, let us say t is in interval 1 to 2. So, this could be our vector function. So, like this we can define several types of vector functions, and they are how to say how we represent them using I, j and k, their domain, where for example, where the variable t belongs to, things like that. All right. So, now what do we mean by, let us say, scalar field and vector field? So, scalar field and vector field, scalar field and vector field. What do we mean by them? So, scalar field is basically, so if to each point p x y z of a region R, let us say of a region R in space, there corresponds a unique scalar f of p, then f is called a scalar point function, and we say that a scalar field f is defined on R, right, on R or in R, basically of a region on R is fine. Yes. So, if for every point p in that region R, if we can correspond a unique scalar f p, so then in that case that is unique scalar is called as the scalar point function, and we say that a scalar field f is defined on R. So, similarly, so for example, we have f x y z. So, for example, if we have x y z equals to, let us say, x square y cube minus 3 z square. So, this defines a scalar field. So, this defines a scalar field. All right. So, next we define the vector field. So, if to each point p x y z of a region D, let us say, in space, there corresponds a vector, a unique vector actually, a unique vector f p then f is called a vector point function, a vector point function, and we say that a vector field f is defined on R, or sorry, on D. So, defined on D. So, that is how we define a vector field, and a possible example could be, let us say f t equals to 3 t square I minus 2 t j plus e to the power t k. So, this defines a vector field on the given domain actually. So, we can have any domain and then this will actually be defining a vector field. All right. So, that is how we define the vector field. Next we have is, so we know in the similar fashion we can define all sorts of vector functions. So, defining the vector function and having its domain of definition is really not a very complicated thing. So, those things are very can be done very easily. Now, the next topic, we know that from function of scalar variable, scalar functions actually, after the function we study usually the limit of scalar functions. So, here also we will basically look into the limit of vector functions. So, how do we define it, what do we mean by it, and we will work out some examples. So, let us start. Limit of a vector function. Of a vector function, not functions. So, usually we know that the limit f t, the function f t is given by f 1 t I plus f 2 t j plus f 3 t k, right. So, when we pass the limit on the left hand side, so we have limit t goes to t 0, that means when t is going to some real number t 0 and I am passing the limit on the left hand side. So, what would happen to the right hand side? How do we define the limits on this f 1 t I, f 2 t j, f 3 t k? So, the idea to define the limit is basically to define the limit in every component. So, we define the limit in every component. All right. So, here are we defining the limits. Now, if I define the limits, then this should be looking like this is the required way to define the limit. So, we pass the limit on individual components. So, suppose after making t goes to t 0, our f 1 t will be f 1 at t 0 times I, f 2 t at t 0 times j, and f 3 t at t 0 times k. So, this is how we define the limits on individual components. So, we can look into an example. So, find the limit of, let us say, f t equals to e to the power t I minus e to the power minus 2 t j plus e to the power 3 t k as t goes to 0. All right. So, solution would be we will start like limit t goes to t 0. So, that t 0 is actually 0 f t. So, let me write limit t goes to 0, f t is basically e to the power t I minus e to the power minus 2 t j plus e to the power 3 t k. So, now we will pass the limits in individual functions. So, e to the power t I minus limit t goes to 0 e to the power minus 2 t j plus limit t goes to 0 e to the power 3 t k, right. And now we will pass the limit on individual functions. So, let us pass the limit in the first function. So, when t goes to 0, e to the power 0 will go to 1. So, I when again t goes to 0, e to the power minus 2 t will go to 1. So, this is e to the power minus 2 t as t goes to 0 is 1, and then here also it will be 1. So, ultimately this thing. So, that will be the limit of this vector valued function or vector function, not vector valued, but a vector function. So, similarly you can work out some more examples. So, I am just writing them. I think it is very straightforward. So, you may try to do them by your own. So, for example, find the limit of, let us say, f t equals to sin t I plus cos t j plus t plus 1 k as t goes to pi by 2. So, when t goes to pi by 2, we will pass the limit, then this will be 1, this will be 0, this will be pi by 2 plus 1. So, ultimately the answer will be I plus pi by 2 plus 1 times k. So, basically the component of j, so or component of any unit vectors, if it is 0, then we do not write that vector. So, we simply avoid that vector, that unit vector basically, that or that particular component, and we write the remaining two components as a plus symbol, and it is understood that the component of the missing unit vector is basically 0, and that is why you are not writing it. So, here in this case at t is equals to pi by 2, this is becoming cos pi by 2. So, cos pi by 2 is 0. So, basically we do not write the jth component. So, we just write ith and kth component, alright. And yeah, and there are some other ways to denote a vector function or to denote a vector quantity. So far we have been writing f t equals to f 1 t I f 2 t j and f 3 t k, but we can also write. So, there are several other ways to write it. So, we can also write f 1 t comma f 2 t comma f 3 t. So, like a point, a point in 3 dimension, or we can simply write f 1 f 2 f 3. So, all these are just equivalent ways to write this vector function in commas basically. So, it is up to you, and in several books you may find the first notation, you may find the second notation, or you may find the third notation. There can be some other notations as well. They basically mean this first line here, that you have component wise addition of these scalar functions multiplied by this unit vectors I, j and k respectively, and also you should not change the order. So, if you write f 1 t, f 2 t, f 3 t, that means the component of I or the coefficient of I is f 1, coefficient of j is f 2, and coefficient of k is f 3. So, don't how to say play with the order of this notation, all right. So, in a function of scalar variable, or in scalar functions, we learnt about limits but we also learnt about their epsilon delta definition. So, epsilon delta definition is something like for scalar function is if we have f x going to L as x going to a, then we usually then this implies that then we usually used to write that for every epsilon positive there exists a delta positive such that we had f x minus L is less than epsilon whenever 0 less than x minus a less than delta. So, this was our epsilon delta definition for the function of scalar variable for when f x is going to L as x going to a. Now, in case of function of vector functions, basically we can have the similar epsilon delta definition as well. So, I can write epsilon delta definition, epsilon delta limit definition, epsilon delta limit definition of a vector function. All right. So, the definition goes like this: a vector function f t is said to tend to a limit I when t tends to a if for any positive epsilon however small or arbitrarily small however small there exists a delta positive or a positive number delta such that our f t minus I, so I is also a vector, is less than epsilon whenever 0 less than t minus t 0, or in this case we have a. So, t minus a is less than delta. So, this is and if this is true, then in that case we write simply limit t goes to a f t equals to I. So, it is not L, basically it is I. So, this is basically our epsilon delta definition for the limit of a function. So, if we say that the function f has a limit, let us say I, then in that case as t tends to a, then in that case for any positive, not position, for every positive. Okay. So, for any positive epsilon however small, there exists a positive number delta such that f t minus I is less than epsilon whenever t minus a less than delta, and we basically write limit t goes to a f t equals to I. So, this is how we define the limit of a function using the epsilon delta definition. Similarly, so like limit of scalar functions, we had several properties. In case of limit of vector functions, we will also have several properties. So, I can just summarize them in a small theorem. So, if f t and g t be two vector functions or R, f t and g t are two vector functions of scalar variable of scalar variable say t, then the following holds. So, what are the following? First one is limit t goes to t 0 vector function f t plus vector function g t is equals to limit t goes to t 0 f t plus limit t goes to t 0 g t. So, the limit of the sum is equals to sum of the limit, all right. Now, similarly, if you have a subtraction, so the limit of the difference is equals to difference of the limit. So, this is also true. Now, if we have let us say product, so the product of two vector function which could be scalar product or a dot product, then it will be. So, if you have a scalar product, we simply do not have product in vector functions. We either have scalar product, which is also called as dot product, or the cross product. So, if you have let us say a dot product of two vector functions and their limit will be equal to limit t goes to t 0 f t dot product with limit t goes to t 0 g t. So, that means limit of the dot product is equal to dot product of the limits. Similarly, limit of the cross product is equals to cross product of the limit, all right. And the third and fourth property is basically limit t goes to t 0 phi t times f t is equals to limit t goes to t 0 phi t times limit t goes to t 0 f t, where phi is a scalar function, phi is a scalar function. So, that means, if you have a vector function multiplied by scalar function and if you take the limit, then basically limit of the scalar function times limit of the vector function. So, that is what we get after taking the limit. And fourth result is limit of the mod basically is equals to mod of the limit. So, limit of the absolute value is equals to absolute value of the limit. So, whatever we will get after calculation. So, these are the results which also holds for the vector functions, and the proof is we will basically prove it using the epsilon delta definition, and it follows on the similar arguments for the results of the based on the results on scalar functions. So, I am not proving these results, and also they are not important from the context of the syllabus. So, these are the results which we will be using quite often. I mean, for the interested readers, you can look into any vector calculus book suggested by me, and there you might be able to find the proof as well. But these are the results which are valid in case of vector functions as well. Now, in the next class, we will start with the continuity of a vector function, and probably we will also introduce the concept of differentiability of a vector function. So, I will stop here for today, and I will see you in the next class. Thank you.